Hello, today I want to talk about Fermat's theorem and how interacting with second derivatives, right? Taking a derivative of a function and then differentiating that derivative to get you a second derivative, how that can be used to sniff out maxes and mins of functions. Here are the two key facts. One says if f prime of c equals 0 and f double prime of c is greater than 0, then f has a min at c. So what is going on here? Well, honestly, just think of a key example. Whenever you hear the phrase min, think of f of x equals x squared. This should be the canonical picture of what a min looks like, right? Think of this at the point 0, 0. So this, right, this is has a min, right? Not by any reasoning from calculus, just I know what the graph looks like. It's y equals x squared. I know what that looks like. I know the min is at the origin, right? So keep this example. It always helps to have those canonical examples in mind, especially in calculus, right? Think of x squared, x cubed, square root, cubed root, sine x over x, sine of 1 over x, right? Keep those functions and their graphs in mind. That it will really help you understand the theorems, running those examples through those theorems. So here is our canonical min. Well, what would happen if you did a first derivative of this function? You'd get 2x, which is 0 at 0, right? F prime of 0 is 0, which is good because this is, see the slope here, right? The slope would equal 0. This is actually Fermat's theorem, right? Because this is by Fermat's theorem. Because if you have a min or a max, then at a differentiable point on the curve, Fermat's theorem implies that the derivative is 0. Now, what Fermat's theorem did not guarantee was max or min, because you could have saddle points from, say, x cubed, right? Again, those canonical examples, always reference those. So now think about, this is where the second derivative comes in. So this is why I care about a twice differentiable function, a function whose derivative of the derivative can be taken. Well, here I'm taking a derivative of 2x. So the derivative is 2. So f double prime at 0 is still 2. It's a constant function. And this is positive, right? Well, that's exactly what we were saying, is that a positive second derivative implies a min, right? So the canonical example you want to have in your head is x squared, which has 0 first derivative and positive second derivative at the origin, right? Now, this is, of course, not a proof that the result is always correct, but it's that key example. So what this is saying is it's saying maybe some different function f can still behave like f of x equals x squared, in the sense that it could have a horizontal tangent line and a positive second derivative, that it at the point C, it's behaving like f of x equals x squared. And this is something you'll make a lot more formal in calculus 2 when you define degree 2 power series approximations. But for now, we can leave it at that level of connection, right? So similarly, in this case, what would the canonical example of a max be? Always keep f of x equals minus x squared. Keep that at the origin. Just take this and turn that parabola upside down. Oh, see, I should have done these in the opposite order, so that I could have said turn that frown upside down. Turn that smile upside down just doesn't rhyme, right? Hey, maybe that's a good thing, that turning a smile upside down doesn't have a nice ring to it, right? So here's our second example. Right, again, horizontal tangent at the max. That's promised by Fermat's theorem, right? Fermat's theorem tells us that there should be a horizontal tangent line at the max. And you can calculate this, right? F prime here would be minus 2x. And f prime at 0 then is 0, right? And furthermore, if you do the second derivative, I'm doing the derivative of negative 2x is just negative 2, which is a constant function, right? So I get f double prime of 0 is still negative 2 because I There's no x on the right-hand side of the formula. So it doesn't matter what x value you plug in on the left-hand side, you always get -2 on the right-hand side. So there's our min, and look at what we said. We said, sorry, there's our max, right? Look what we said, the max here, max at C, right? Corresponds to what? The max, which is what we have. We definitely have a max just because we know the graph, corresponds to a negative second derivative. That's exactly what we're saying here, right? So a negative second derivative corresponds to a max. So keep those two examples in your head: x squared for a min, negative x squared for a max, and that will help you remember how these second derivatives work, right? Positive second derivative, like x squared, causes a min, like x squared has. Negative second derivative, like negative x squared, has a max, right? Now, that is our method for, those are two small examples, right? Let's now look at a more complicated example. Let's test out this framework in a more complex example. So let's consider the function f of x equals e to the x plus e to the minus x. I'm going to look at this function, right? And in particular, I want to find all horizontal tangents and for each attempt to classify, right? Try to classify as max or min via a second derivative. And why do I just say attempt? Well, you might notice up here, what case was not up here? We had two cases. We had positive second derivative. We had negative second derivative. I never said anything about second derivative equals 0. It's because if the second derivative equals 0, it doesn't tell you anything. It could be a max. It could be a min. It could be a saddle. I don't know. So, right. So positive derivative equal to 0 would not tell you anything. So that's why I said try. Just try. Okay. You might get 0 for the second derivative, in which case the test didn't help us. This happens, right? This will happen. But in this case, it's going to be an example where we can use it because I want to show the technique. But I just wanted to comment that mathematically, it is possible for the second derivative to be 0, and then it might not give you any information. So meanwhile, let's try this out. So, and this function, this is, e to the x plus e to the minus x. I don't immediately have a sense of, I don't immediately have a graph that just pops into my mind here, right? So we're really using the derivative and second derivative to learn a lot about the graph. So here, what I could do is I can say that the first derivative, I could take that by applying what property? Well, I'd start with linearity, right? So I'm going to take the derivative of each term separately. So I'll use linearity. Then the first term is one of our basic derivative formulas that we just want to memorize. The derivative of e to the x is e to the x. The second formula is a chain rule, right? So this is, well, let me write that out a little more. This is a chain rule. So this here, I had this first step was because of linearity, right? The fact that derivatives distribute over addition or subtraction. This was by chain rule. So I took the derivative of the outer function, e, which stayed the same. I left the inner function alone inside that outer prime. And then I multiply by the derivative of the inner. Those are the 3 steps of chain rule, always, right? Then I can evaluate the derivative of negative x. It's -1, right? It's just a constant -1. And I can move that out front just to clean it up a little bit. So it's just cleaner to say e to the x minus e to the negative x. So remember what our goal is. I wanted to find all horizontal tangents. How do you have a horizontal tangent line? Well, you want the derivative to be 0. So set the first derivative equal to 0 in order to find horizontal tangents. So what do we need here? I need e to the x to equal e to the minus x, right? Just move that over the other side. Then if you want, you can take natural log of both sides. right? Or equivalently, use the fact that e is a one-to-one function. The exponential function is one-to-one, either one. And I get that x equals negative x. And there is only one number who equals its own negative. That's 0, right? 0 is the only number equal to its own negative. So the solution to that equation, x equals negative x, is x equals 0, right? So we got just one critical value, right? Just one place where this is the location of the horizontal tangent, and actually the only horizontal tangent. And up front, maybe there could have been more. Maybe there were multiple horizontal tangents to this graph. I didn't really know until we did the derivative and set it equal to 0. So I now know something about this graph, right? I now know that this graph, I don't know what it does globally, but I do know that at the point 0, 2, and where's the 2 coming from? Well, I can take that and plug it back into the original function, right? The original f, to get the y coordinate, right? So 0, 2, that's a point where our graph has a horizontal tangent line, slope 0. Right? So that's what I found here. Now, next, what I can do is I can look at the second derivative, because I don't really know at the moment if this is a min or if it's a max, right? I don't know that. And in fact, maybe it's a saddle, right? I don't even know that. Maybe it's neither. So, but I'm going to use the second derivative, and hopefully it tells me something. Hopefully the second derivative is either positive or negative, and then I'll know. Then I'll know which one it is. So let's calculate the second derivative to determine. All right, so the second derivative, what am I doing there? Well, now I'm differentiating the first derivative. That's what second derivative means. It means the derivative of the first derivative. And I already have a formula for the first derivative. It's e to the x minus e to the minus x. Well, this calculation is actually extremely similar to what we had the first time. Apply linearity. Right. Then apply the chain rule. Well, when you do the chain rule, by the same logic as last time, we're going to get, on this piece, we're going to get negative e to the minus x. You can write out the intermediate steps if you want. E to the minus x times derivative of minus x. But here I'm jumping right to the same thing we got last time, since it's the same derivative. Double negative becomes a positive. So f double prime is actually equal to the original function, right? By coincidence. That doesn't have to always happen. That's kind of special here for e to the x and e to the negative x and combinations of them, linear combinations of them. But f double prime of x, we now have a formula for it. So now I can evaluate that at 0, at my critical value, right? And I can say, oh, this f double prime, this is 2, which is positive. My second derivative is positive. So now think way back to the beginning. Those two examples, what one has positive second derivative? X squared, which has mins, or negative x squared, which has a max, right? Well, this is positive, which corresponds to the graph of x squared. What does the graph of x squared look like? It looks like this, right? So this has the same second derivative as x squared, which means we have a min, because x squared has a min, right? So keep those two key examples in mind, and you'll never get mixed up as to the second derivative and how it classifies things, right? So this is a positive second derivative. Therefore, I now know that my graph has a min. And in fact, I know that locally, at least nearby, it's actually going to look like x squared. It's going to look like a little upward facing parabola on my near that point, because I knew the first derivative was 0 and the second derivative was positive. That tells me that near that point, I'm going to get an upward facing parabola. So there we go. Now I did it. I classified this as a min, right? So that tells us that 0, 2 is a min for this function, right? Of f of x equals e to the x plus e to the negative x. Now, it doesn't give us the rest of the graph, but a little bit of reasoning can. This, if you think about it, the end behavior, this kind of gave us the local behavior. What is the end behavior of this graph? Well, if you think about the limit as x goes to infinity of this quantity, what's going to happen? Well, this goes to 0 because I'm taking e to really big negative powers, whereas this goes to infinity, right? So I have infinity plus 0. Oh, okay. Well, so this goes to infinity. How about if I do x, the limit as x goes to negative infinity? Well, this, what would the end behavior on this be? This would now go to 0 because now I'm taking e to negative powers on that term. And here I have a double negative in the power, which is positive. So e to the really large positive number becomes infinity. So 0 plus infinity, again, is infinity. So the and behavior, you could say, is up, up, and behavior, right? If you wanted to talk about it in sort of pre-calc terms. Or you could just say that the limit as x goes to infinity is infinity, the limit as x goes to minus infinity is infinity. If you put all this together, this actually gives us a really good sketch of the graph. It goes to infinity this way, and it goes to infinity this way. There we go. That's basically what that graph looks like, right? It's kind of a steep paraboloid looking thing. It grows actually a little faster than a parabola grows. E to the x grows faster than x squared. But basically, from a mile away, from outer space, it looks like a parabola, right? And it does have a min there at that point, 0, 2. So not only have we classified the only max or min of the graph, but when you couple that with end behavior, at least in this case, we know the whole graph, right? So it's a powerful framework. Great. All right. So that's how you can use second derivatives to classify extrema, right? To find maxes and mins, and be certain of the point being a max or min on your graph. Great. Thank you so much.